So now we move into a chapter. It's ideal gas mixtures. Chapter really has two halves. The second half is a particular one of interest to a lot of engineers, a lot of mechanical engineers, and it's the study of moist air. That's called psychrometrics. I don't know if you would have guessed it, like that's the study of moist air, but that's what that word means. Psychrometric applications, and it impacts our comfort. We're going to have both a molar description and a mass description. We'll talk about the partial pressure in an ideal gas. We'll talk about the partial volume, and then we'll be talking about how do we make changes or calculations for the change of energy, internal energy, as well as enthalpy, entropy. How do we get average properties like specific heats for ideal gas mixtures? And then we can go back and we can revisit and we can solve problems. Closed system analysis, piston, cylinder, but now it's a mixture of ideal gases instead of a single. Or we can do open system analysis, flow of mixtures through nozzles, turbines, compressors, the game. So the mole fraction. So we say that our components, we're going to have component, let's say 1, 2, 3, ... We'll talk about the number of moles of 1, the number of moles of 2, and the number of moles of 3. And if we add up the number of moles or number of kilomoles in a container or a cubic meter, some specified volume, then we can get the total number of moles. Notice N. What is that for? The amount in moles or kilomoles. What's the subscript on it mean? That component. So sometimes they'll say Ni. Oh, I is 1, 2, 3, or how many components you have. And then what happens if you have no subscript? That means it's of the mixture. So sometimes I'll write N of the MIX, but this book usually just, if it leaves off the subscript, and you're talking about gas mixtures, it means it's of the mixture. It's the sum of all the components. All right. Now, the mole fraction, if you take this equation right here, and you divide the whole equation by N, you didn't change it, but what you get is 1 is equal to, and then they call this Y1, and they call this Y2, and they call this Y3. And so Yi is the number of moles of that component divided by the total number in the mixture. It's called the mole fraction. That's pretty easy. Now, a lot of textbooks not only talk about the mole fraction, they'll talk about the volume fraction. All right. Well, if it's always behaving as an ideal gas, you can get that the volume fraction, V1 plus V2 plus V3, those would be volume fractions, sum up to the total volume of the mixture. All right. And the volume fraction, VI, will be the total volume times the mole fraction. Or another way of saying it, the mole fraction is the volume occupied by that particular species divided by the total volume. It's the mole fraction's equivalent to the volume fraction for ideal gas mixtures. So sometimes somebody will say, well, by volume it's 10% this, 20% this, 60% this. Well, they just told you the mole fractions, even though they said by volume. Another way to describe a mixture is by mass. Okay, well, how do you relate mass and moles all the way back in chemistry? Big M, the molecular weight or molar mass. So that'll be the number of kilograms per kilomole of our particular species. So if we have species I, maybe it's oxygen or nitrogen or argon. And you would have a particular molar mass for that nitrogen, oxygen, or argon. And you can look it up in the tables and probably recall values pretty well as well. So it's the that's the mass per amount, kilomole. So if I wanted to, I'd say, well, it's the mass of the species I divided by the number of moles of species I. Isn't that what the molar mass is? We like to think of the mass per 1 kilomole, like For oxygen, it's 16 and 16, around 32 kilograms of oxygen per kilomole. All right. How do we go back and forth between mass fraction and volume fraction? Do it with a table. Organize your work so it's easy to track it. I would set it up this way. I would say, how many different components do I have? Maybe it's oxygen, maybe it's nitrogen, maybe it's argon. And that list could go on. And then we would say, what is the molar mass of argon? What is the molar mass of each one of these? So instead of that, maybe I'd say component, and then the molar mass, and then oxygen, what is it, around 32, nitrogen around 28, argon around 44. But you can look it up. Your memory doesn't have to be perfect, right? And if we want more digits to it, we look it up in Appendix A1. And what do we get for some of these values? Well, you look them up. How's that? Okay. So, and then I'll do this. I'll say, well, what was the mole fraction given to me? Maybe it was 10%, 0.10. Maybe it was 30%, that'll be 40%. And if I only have 3 components, they better add up to 100%, shouldn't they? So those are the Y's, the mole fractions. And so you say, let's assume that N is equal to 1 kilomole. So if I say that N is 1 kilomole, can you now tell me what is N for each of the components? This is too easy of a question. It'll be 0.1 times 1 kilomole. It's just this column had dimensions of dimensionless. This one has dimensions of kilomole. And then this is 0.3 and that's 0.6. If you add them up, guess how many kilomole? Well, you're back to the assumption you had 1 kilomole of the gas mixture. But now I think you're conceptually ready to say, okay, if I have that many kilomoles, 0.1 kilomoles of oxygen, what is the mass in kilograms of oxygen? How do I calculate that? You just, lowercase m is the number of moles times big M, the molar mass, isn't it? So we would take 0.1, multiply it by 32. You can see it's set up easily for a spreadsheet application. And this one would be 0.3 times 28. And this would be 0.6 times 44, right? What is the molar mass of argon? 39.94. Thank you very much. We'll fix that right now. 39.94. I knew it was around 44. Hold it. That's not close to 44. It's close to 40. 39.94. Okay. Now, if I sum that column, what does it tell me? The total mass. This would be the total mass. Now, that's all starting with the assumption of how many kilomoles of the mixture? 1. And so guess what this is also equal to? The mixture molar mass. The mixture molar mass would be the sum of that column. Because by assumption, in my concept, I left it as I start with 1 kilomole. So you could even write the equation. You say the mixture molar mass, M of the mixture, would be what? The sum of YIMIs. It's a mole fraction averaged molar mass. All right. Now that gives us the ability to calculate the mass fraction. Now this textbook, I'm thankful, they introduce mass fraction and they say the mole fraction, we're going to use the symbol YI. The mass fraction, they're going to use MF without a subscript. It's just MF, 2 letters, subscript I. Some books don't like having 2 letters, lowercase, for a symbol, so they say, well, let's pick something else. Let's pick P. Oh no, P has been used for pressure. Okay, how about T? Let's use T. No, T. Some books, unfortunately, have used X for mass fraction, and then guess what X is used for earlier in the book? Quality. So this textbook gladly, I'm glad they didn't do that. But some people may look at it and say, that's kind of a funny way of, no, it's okay, it's mass fraction, MF. All right, so if I want to calculate the MF, the mass fraction, what I do is I take here, I'll write the equation up here is the mass of the component divided by the mass of the mixture. So it would be this 0.1 times 32 divided by whatever came out down here. And then likewise 0.3 times the 28 divided by whatever came out down there. And so you can see how you can calculate the mass fractions. We'll solve a problem in a minute. Sometimes they'll tell you, oh, the molar analysis is 10% this, 30% this, etc. Well, what did they say when they said molar analysis? They're giving you the mole fractions. Sometimes in the textbook, read the textbook carefully. Have I encouraged you to read the textbook? I should every lecture. Hey, read the textbook. But anyway, they use this word gravimetric analysis. Percentages are for a gravimetric analysis. I gave you the mass fractions. So anyway, let's press forward. Now let's talk about the partial pressure concept. We have Dalton's model gives us the partial pressure concept. I just put Dalton's name out there to put it in context of maybe your exposure in chemistry or physics, and then Amagat's model for partial volumes. But the idea is you take a container and it's easy to just think of two components. Think of the reds and the blues, and then we're able to conceptually separate into the same size of the container. So the volume of the container is the same, it's constant in our thought process. But we're able to separate them into two equal sized containers, one containing only all the red and one containing only all the blue, or component 1 and component 2. So the volumes are the same. What about the temperatures? Well, I can tell you right up, we're going to have partial pressures, we're going to have partial volumes. Do you think we're going to have partial temperatures? No, it makes no sense. So there's no concept of partial temperatures out there. I'm kind of glad, because it's easy to think of partial pressures and partial volumes, but partial temperatures? No. So anyway, so the temperatures are going to be the same, or between the two in examples. Okay, so if they always behave as an ideal gas, what you can write down is that the total pressure here is equal to, well, depending on how you want to get it, but what we're going to get is the total pressure is the partial pressure of 1 plus the partial pressure of component 2. So let's say this is all for 1 and these are all for 2, component 1 and component 2. Well, how did we get that? Maybe we start this way. The number of moles total is the number of moles 1 plus number of moles 2. Do you like that? Do you trust that? Does that make sense? All right. Does it always behave as an ideal gas? That's the whole chapter. If it's a real gas, guess what? You need to take another class. Or you just learn on your own. Or you're going to have to get some that's what people typically do, is they get some pretty good software that can do it for real gases. All right, so how do I recall? PV equal to N RT. There's one error in this equation as I've written it. Do you see the error? So it's R bar, isn't it? So what we can do is come down here, we can replace, this is R bar T, it's here, PV divided by R bar T, right? How about for the number of moles of species 1, we're going to have P, but it's a different pressure inside this container. If you had a little pressure tap right here, what would you be measuring? You'd be measuring P1. If I had a little pressure tap, I'd be measuring P2. Over here, I'm measuring total P. We're going to show that the total P is the sum of P1 and P2, which seems obvious, but let's show it anyway. So it's P1V divided by R bar T plus, and then replace P2V divided by R bar T. And so we just worked using the ideal gas equation. Go ahead and cancel the V over R bar T, and you get what we wanted to show, QED. Almost too trivial, isn't it? There's one other thing that we want to show, and that is that the partial pressure of each component, let me just say I, is equal to the total gas pressure times the mole fraction. Not the mass fraction, but the mole fraction. Okay, well, how do we get that? Well, maybe we start with that P I is equal to PI. That looks like a good equation. I have a lot of confidence in that equation. It's written correctly. I haven't made a mistake yet. And then what is PI if I use the ideal gas equation? PI, VI, NI, TI, right? So we could replace PI by by NI R bar T I divided by VI, right? But we're using Dalton's model, so we have the partial pressure concept. That we really should drop the subscript on the VI and just talk about the volume. Likewise, drop the subscript on the T. There's no concept of partial temperature. And in this case, we're not talking about the partial volume. We're talking about the total volume. Okay, well, I used the ideal gas equation as if I'm applying it to one of the species here, but I can also use the same ideal gas equation that PV is equal to N R bar T. This difference is this is the total number of moles in the mixture, and this is the total pressure of the mixture. So what we'll do is we'll say that equation's true, so I'll rewrite this equation to be PV over N R bar T, that's equal to 1. Let's then multiply by 1, which is PV over N R bar T. Cancel the R bars, cancel the T's, cancel the V's, and we got what we set out to show, QED, that PI is equal to NI over N, that's the mole fraction YI, times P. Look good? You use this a lot. All right. The next one is Amagat's model with partial volumes. Here what we do is we have the total volume initially, but it's equal to a container that's smaller in size plus a container that's also smaller in size. But the sum of the two volumes is equal to the original volume of the gas mixture. But what's in the first volume is only that species 1, and in the second volume only the species 2. Did I show them that they look different sizes, or do they look too close together in size? They look different enough? Good. And so what's the same, though, is the pressure is the same. And we already said the temperature is the same. And so the idea of the partial volumes is just like that, that you have V is equal to V1 plus V2, and you can show that the VI, the partial volume of a component, is equal to the mole fraction times the total volume. So somebody said the molar analysis is 20% of this species in the ideal gas mixture. By volume, it's 20%. It's occupying 20% of the volume. Okay, the mole fraction is the same. All right, I'm going to press forward here. Let's just start using some of these numbers. So we have the molar analysis of a gas mixture with 15% nitrogen, 20% CO2, and 65% methane. Are those percentages the mass fractions or mole fractions? It's the molar analysis. It's mole fractions. Those are the Y's, not the MF's. The gas mixture is at a total pressure and a total temperature. Determine the mixture molar mass. The mixture molar mass. How are we going to calculate cap M? Sometimes I put MIX as a subscript, but I don't think the book does. So what is the equation? Yeah, just the Yi and the molar mass of each of the components. Well, I did that. I set it up in an Excel type of spreadsheet. You can do it on exams, a nice little to help organize the work. And I would do the same thing. I'd say I have component 1, component 2, component 3. First component's nitrogen, the second component's carbon dioxide, third component's methane. And I look up the molar mass of each of those components. So for the nitrogen, it's 28.02. And sometimes it's better to put the symbol and then below it the units, kilogram per kilomole. And then for the carbon dioxide, 44.01. And the methane, 16.04. And then I put in the given mole fractions, which are dimensionless. So it's 0.15, 0.20, 0.65. I double check. Does the sum equal 1? Yes, and I'm good. If it didn't, I have a problem. That something's left out. Then we'll take and multiply y times m. And because that has units, I'm going to put y times m. And what are the units if I multiply y times n? Yeah, that's kilogram per kilomole. And then, so let me write some of the numbers down here. It would be a 4.2015, 8.802, and 10.426. And if I sum that column, it gives me the molar mass of the mixture. And we calculate the molar mass of the mixture that comes in at 23.4295. Too many digits. Let's put 4 digits, significant digits. Does the molar mass have units? Kilograms per kilomole. Part B, what is the gravimetric analysis of this mixture? Well, I calculate the mass fractions. So how do I calculate the mass fractions, which are dimensionless? That's right. So it'd be 4.2015 divided by 23.42, wouldn't it? And it would be the 8.802 divided by the 23.42. And so it's very easy to set that up. When you come in here with the mass fractions, this turns into 17.9%. This turns into 37.6%. And the last one's 44.5%. It's shifted around because it was a lot more methane by on a molar basis, but on a mass basis, because methane's so light, the percent went down because it's light. Methane is light. All right. So there's a column right here is the answer to part B. That's our gravimetric analysis. What is the partial pressure of the CO2? Yep, that's exactly it. So the partial pressure of the carbon dioxide will be Yi, the mole fraction of the CO2, times the total pressure, which was 240 kilopascal. And so we calculate the partial pressure of the CO2. It comes in at 48 kilopascal. That's the answer to part C. Now, the volume occupied, if you had 1.8 kilomoles of the mixture, and they want that volume in units of meter cubed. So I said, I have this much mixture, 1.8 kilomoles of the mixture. What is the volume occupied? There's a couple of ways of doing it, isn't there? There's not, usually when you have this, a couple ways to solve it, but if they've given me N is equal to 1.8 kilomole, I already have the molar mass, but I don't really even need that. What PV is equal to N R bar T, so that the volume is N R bar T divided by P. Make sure I have absolute temperature, absolute pressure, R bar. What is the numeric value of R bar? Very good, 8.314. So kilojoules, kilogram, all that. Let's go ahead and, I believe you can finish this off. So the volume is going to be 20.58 cubic meter. Partial volume of nitrogen in cubic meter, in the 1.8 kilomoles of the mixture. So now they're saying, give me the partial volume. So how do I calculate the answer for part E? This is the answer for part D. That would be the partial volume of the nitrogen. Is that the mole fraction of the nitrogen times the total volume of the mixture? Sure. And so the partial volume of the nitrogen comes in at 3.087 cubic meter. Again, conceptually, you want to think about this. Okay, I have this mixture, and if I really only put nitrogen, pure nitrogen, at the same pressure and the same temperature as that mixture, it would only occupy 3.08 meter cubed. Okay, last part. What is the volume occupied if you had 62 kilograms of the mixture? So you could go back to ideal gas equation. You could go PV equal to M R bar divided by the molar mass of the mixture, T. Would that work? You get pretty good at the ideal gas equation, don't you? Hey, the whole chapter is ideal gas mixtures. So you calculate that the volume occupied by 62 kilograms comes in at 30.25 meter cubed. The next page has all the numbers again on an Excel spreadsheet. So let me switch to that. So here's the answer, part A, B, C, D, E, and F. Here's B right here, I should say. All the mass fractions. You can see I played with it a little bit more. I did all the partial pressures. I did all the partial volumes. I did the masses and then calculate the moles and the total volumes, or the volume fractions, or the volumes, partial volumes. Okay. Once we have a good description of ideal gas mixtures, we need to be able to describe changes in internal energy, changes in enthalpy, changes in entropy. And in order to do that, we want to be able to do it both on a per mass basis as well as a molar basis. So let's kind of divide the world in half, and this will be the mass half, and this will be the molar half. And let's just focus on the change in the total. I forgot, what is cap U? Is that the change in the total entropy? Internal energy. So if I wanted to calculate it, I'd say, well, it will be the mass times the change in the specific, right? But if I have multiple components, let's sum over all the components like that. Does that make sense? That's just an easy extrapolation. Okay, I'm just going to add the contributions of the change from each of the components. A lot of times we're very much interested in using constant specific heat. Should I use CV or CP? CV of that species, and then I have the final temperature minus the initial temperature times the mass of the species, sum over all the components. Does that equation look good? That's exactly how you calculate the change in the total internal energy of the system. Somebody says, I sure would like to use the total mass of the mixture times some CV of the mixture times T2 minus T1. That looks reasonable. So what you do to get the CV of the mixture is all you have to do, do this, put the MI right there. Let me put divide by divide by m, and multiply by m. See how I introduced m over m right there? But that didn't change anything. The equation's still true. But this mi over m is the mass of the species I divided by the mass of the mixture is the mass fraction. So, and this m, because it's in every term, can come outside the sum. And so what you pick up is m times the sum of the mass fraction of each component times the specific heat constant volume of each component times the T2 minus T1. And then you say, oh, I see the analogy, or I can now see what the appropriate mixture specific heat on a mass basis is equal to the sum of the mass fractions times the individual component specific heats. We could do it for the change in enthalpy. It would get C sub P of the mixture is equal to the sum of the mass fractions of each component times C sub P of each component. True? Can you guess what it's going to be over here for a molar description? C sub V mixture equal to the sum yi C sub V of I, but there's something missing in this equation, and you need to let others participate. Somebody else here, I need to fix this equation. I moved from mass fractions to mole fractions. I really have two errors I need to fix in two places on this equation. Do you see what I need to do to fix it? Good try, good try. It's a very simple notation. Oh, come on now. He guessed. He gets a little gold star for guessing. Somebody else, just guess. It needs to be on a molar basis, that's right. And so what were the units on this CV right here? Kilojoules per kilogram Kelvin. What do you put the bars on? Is that now some sort of averaged? In some books, when they put a bar over, they say we averaged. But in this book, when they put a bar over, what does that mean? It's on a mass basis. That's right. It's on a mass basis. So guess what? The units of CV bar are kilojoules per kilomole Kelvin. Right? And then the same thing for the specific heat constant pressure, C sub P of the mixture. I think the book actually doesn't put MIX. It's like if I leave it out and I'm talking about an ideal gas mixture, you know it's for the mixture. And if I put a subscript I, that's for the component in that mixture. But anyway, this is equal to the sum of YI C sub P I bar. What's the relationship between R and R bar? Maybe you were right. You were to use the molar mass, right? Yeah. So R is equal to R bar divided by the molar mass. What's the relationship? I need to scroll down a little bit between C sub V and C sub V bar. Yeah. And then C sub P is equal to C sub P bar. Once you got the pattern, it's almost too easy, isn't it? Well, you can do the same thing here, and you would say, okay, we have the change in the internal energy, but it's going to be the sum of the number of moles of each component times U bar 2 minus U bar 1 of that component. What's the bar again on top of the lowercase u? It's on amount, yeah, per kilomole instead of per kilogram. And then you would do the same thing, the steps right here. I'm going to say that you can do that. You can fill in those little details. But the bottom line is where you want to get to, okay? Either you do a mole fraction average of the specific heats or a mass fraction average of the specific heats. All right. Okay, life was easy. Now we have to deal with the change in entropy of an ideal gas mixture. First of all, review how do I calculate the change of entropy just of an ideal gas? Forget about mixing the ideal gases. What was our basic equation? Yeah, so basically, let me kind of review right here. This would be the mass times lowercase s2 minus lowercase s1, which would be mass times a C sub p natural log of final temperature over initial temperature minus R natural log of P2 over P1. Does that equation make sense? And if you say I have a mixture, all we do is we now want to sum over all of those components. They have an individual mass they contribute. They have different specific heats. Do they have different temperatures? No, don't ever go for a partial temperature concept. It's not out there, nowhere to be found. We have partial pressures, we have partial volumes. Okay, how about this R? Is that of the individual component? Should I put an I subscript on that or not? That's right, it's R bar over the molar mass of that gas. So yes, we put an I on it, subscript. What about these P? Do we put a P2I and a P1I? Well, we didn't put a T2I for sure, but do I do it for the P's or not? Yes. And that's the hard part. And that is really the hard part. It is. Because what am I talking about? Well, you almost need to do two things, two analysis, but let me finish this up. If I do this, if I take and I multiply by m here and m there, then I have this is a mole fraction, the mass comes out, so basically the mass times the sum of the yi times c sub pi natural log T2 over T1 minus ri natural log P2i over P1i. Did I do that right? Okay. Now, there's two cases that you have to handle. The easy one is that I have, let's say, just a compressor or a pump. And so I have the in and I have the out. And tell me, do you think the molar analysis changes between the input stream 1 and the output stream 2, and I'm going to do an open system analysis for this. Do you think the molar analysis changes? No. All right, next case. I have an input stream and an input stream, and they mix with one output stream. Yes. This is where the molar analysis of the first input and the second input typically are not the same. Hence, when they mix, you don't get the same on the outlet. You get some averaged, right? So what you need to do is in your mind when you have to compute changes in entropy, think. Because this term right here is the hard part. This P2I divided by P1I. Is it equal to yi times P2 divided by yi times P1? Yes, that's exactly what it is. And if I come over here for this type of analysis, I boosted the pressure. P2 is typically a lot greater than P1, but I didn't change the y's. And because of that, in that case, the yi P2 divided by yi P1, these pretty much cancel, and this term is simply the ratio of the pressures. You think, oh, this is easy, entropy. And then they give you a mixing problem. And then you go, huh? Well, in the mixing problem, typically the pressure 1 is equal to the pressure 2 is equal to pressure 3. You're just mixing them. You're not changing the pressure. Well, in that case, what happens, let's take a look. You'll get the, and now I know that I'm doing it only from, let's say, 1 to 3. Okay? I'm just going to focus now on, sorry about the syntax, maybe I should have called this 3 in that state too, but doing 1 to 3, the change in the entropy going from 1 to 3, and then I'll have this P3I divided by P1I, which is P3I is going to be the mole fraction of I at the exit 3 times P3, and then this is the mole fraction of at 1 times P1, and if they're just mixing constant pressure, the pressures cancel, but not the Y's, because they changed. And so you have to calculate those changes and put those into the change in entropy calculation.
So would that be for both Dalton's model and Amagat's?
Typically what we do is we only use partial volumes when we're thinking about a different way of expressing a molar analysis. They say the volumetric analysis showed, but we heavily use partial pressures. So just kind of tuck partial volumes off to the side, and we really want to dominate partial. Because you're right, you could come in here. Do you remember the other equation for change of entropy? Wasn't it something like CV natural log T2 over T1 plus, not a minus, R natural log V2 over V1? And yes, you can work with partial volumes, but let's not do that. Okay? That's like trying to speak 5 languages. Let's just get 2 languages. Let's get molar and mass, and let's just stay with pressure, partial pressures. Okay. I don't think I have time to solve this problem. So what I'll do is I'll stop, allow you to pick up your graded exams if you didn't pick it up already. Thank you for your attention.